This is the second day of this unit, but we skipped the first day, so it's the beginning of the unit for us, which has all the definitions. So um, this is all about graphs, and it's not like the way that we've been thinking about graphs with like an XY, coordinate plane. So in a really basic sense, what we're talking about is a graph is basically vertices and edges, and they have to be connected in some way. That's what this means. Well, connected is kind of a loose term. So all this is really saying it has to have a finite set of vertices, a finite set of edges, and then there's an edge endpoint function that maps each edge to a set of vertices or to just itself. And we'll see what this looks like in a second. Here's some more definitions. You can read through these. Adjacent vertices are two vertices connected by an edge. So that could look like, vertex 1 and vertex 2 are over there, and they're connected by an edge. And so this would be adjacent vertices. Adjacent edges are two edges with a common endpoint. So like endpoint, maybe there's another vertex over there, and there's another edge. We could call this edge 2. This would be edge 1. Edge 1 and edge 2 are adjacent edges then because they share a common endpoint or a vertice. Parallel edges are vertices that are connected by more than one edge. A loop is basically something that goes to itself, an edge that goes to itself. It shares its own vertex. So like a loop could be like that. That's like edge 3. So even though it's like round, it's still called an edge. Parallel edges, sorry, would be you could have another one that goes like this, another edge 4, and then edge 1 and edge 4 are parallel edges, they're called. So again, a little bit different than we're used to knowing about the word parallel, but they just share the vertices share two edges. Okay, an isolated vertex would just be like, maybe I had vertex 5 over here, and nothing's touching it. It's isolated. Simple graph is a graph with no loops or parallel edges. So this up here has parallel edges right there, so it's not simple. It also has a loop, making it not simple. So that's a simple graph. An adjacency matrix is showing you how they're connected, how vertices are connected to one another. So we could draw this given our adjacency matrix. So it just means that, like, well, we have vertex 1. You can draw these wherever you want. Let's say this is vertex 2. This is vertex 3. And then you see that vertex 1 has goes to itself one time. Okay, so this could be, it goes to itself. So vertex 1 to vertex 1, there's one edge. And it's just got to be a loop because it goes to itself. Vertex 1 goes to vertex 2 twice. So there's two edges. So that would have to be, edge 1 there. And then there's another one that goes there, another edge. Vertex 1 does not go to 3. 2 goes to 1 with two edges. We already have that written down though right here. 2 goes to 1 with two edges. And then 2 goes to itself twice. So you would have to draw two loops here. So like maybe there's a loop. There's a loop right there, and you guys have there's another loop. And vertex 3 doesn't go anywhere. Nothing touches vertex 3, it's isolated. Alright, so here's another edge endpoint function. This is kind of what it looks like another way. This is the function. So we know that if you look at all the endpoints, the vertices, you'd say that this is like, vertex 1, you have 2, 3, and 4. So vertex 2, vertex 3, and I'm just putting it in like a little square, but this is going to be weird in a minute. So edge 1 is going from vertex 1 to vertex 2. And they don't have to be straight lines. You could draw them a little boat if you want, because we're not sure if we have parallel ones yet. Edge 2 It only has one endpoint, which means it's a loop. And you can label these with edge 2 is right there. Edge 3 goes from 1 to 3. So I kind of wrote this stuff in the way, but this is going to go right there. That'd be edge 3. 1 to 4 is the next one. That would be edge 4. And edge 5 is 3 to 4. And so this is, all of our graphs could look a little bit different based on where we put our vertices, but this graph fits the criteria of the edge endpoint function. So that's what a graph is, essentially. We could also draw a simple graph with 5 vertices and 7 edges. So you can just do this however you want. I'm going to say that it's got to be simple, though, so no loops and no parallel edges. So 5 vertices, V1, V2, V3, V4, and V5. So 5 vertices and 7 edges. We got the 5 vertices, 7 edges. I mean, I can give 5 edges right now. 1, 2, 3, 4, 5. And we need 2 more, but I can't have 3 go to 4 again because that'd be parallel edges, and that would make it not a simple graph. So I can't have any loops either, but I can go, let's say, 3 to 2. Now I have 6 edges, and I could go, 1 to 5. There. Now we have 7 edges. So again, this one right here was its own vertex. So you'd have 7 edges. 1, 2, 3, 4, 5, 6, 7. Okay, and it's simple because there's no parallel edges. There's no loops. Oh boy. Okay. So this is what's like kind of like a directed graph. A diagraph, it's also called. A, B, and C are 3 cities. There are 2 flights from A to B. And then 1, let's see what this says here. Okay. So we could just draw this here. This is A, B, and C. If we want to draw this out, we can. 2 flights from A to B. So this is, we're going to put these arrows here to show that they're directional. 3 from B to C and 1 from A to C. 3 from B to C. 1, 2, 3, and 1 from A to C. There are 2 flights from B to A, so now this is going to get really messy. That's why we don't really want to draw this out. We can just do it with the matrix. So this is directional though, so we're going to have like A, B, C, A, B, C. Now it should make sense that we shouldn't have any, A shouldn't go to A, because that's just a flight that goes from A to A and it'd be pointless. But there are 2 flights from A to B. So from A to B, this would have to be a 2. It's going to be 0 there. 3 from B to C, so B over to C would be 2. And there's 1 from C to A. Or wait, 1 from A to C. So 3 from B to C. Oops. It'd be 3. Okay, 1 from A to C. And then there are 2 flights from B to A. So from B to A would be 2 flights. 2 from C to B. C to B would be 2. And then 1 from C to A. And then the only things left over is B to B, obviously 0, and C to C, 0, because the flight's not going to go straight to itself, So this would be an adjacency matrix. And it's, you just kind of fill out from row to column, from to. Right, and the last thing, we could do a directed graph with this adjacency matrix. So this is the same thing, just going backwards. If we had, say, vertex 1, vertex 2, vertex 3, and vertex 4, this one says 1 goes to 1. Okay, so this is like, I am going to give it an arrow because this is a directed graph. Okay, 1 goes to 2 twice. So I'm going to kind of give it bowed because these are then parallel edges. 1 goes to 2. 1 also goes to 3. Okay, so we've done all of the froms from vertex 1. Vertex 2 goes from 2 to 3 one time, from 2 to 3 once. And it goes from 2 to 4 3 times. 1, 2, 3. 3 goes to itself twice. And again, if it's going to itself, it just has to be a loop. And then vertex 4 goes to 1 once. And to vertex 2 once. So now you have to also have 1 coming out over here to vertex 2. Alright, so that's a directed graph. Looks pretty crazy, but it's all based on the matrix. Alright, please let me know what questions you have. There's a lot of stuff going on with just weirdness now, you know, like graphs. The edges don't have to be straight lines. You're calling it an edge even though it loops around to itself if it shares its own vertex. So a lot of definitions.